So you missed lesson 4.2.6. This is all about bond energy in reactions. And we have already talked about this a little bit earlier in Unit 4, as well as back in Unit 3 and maybe Unit 2. So some of this will be familiar to you. So it says during a chemical reaction, energy may be released or absorbed. The question for us now is how to understand that energy required or energy released on the particle level. This is a great picture right here. It shows hydrogen gas molecules combining with oxygen and forming water molecules. So you can see that the blue atoms represent the hydrogen and the teal represents the oxygen. These bonds break, so the atoms are separate, and then they form these two water molecules. So looking at the energy diagram here, you can see that the energy of the reactants is right along this line here, and then energy goes in to break the bonds, and then energy is released as the new bonds form, and the products would be on this line right here. And so energy is not destroyed or created, but rather transformed. And so you can see here that the green bars show the chemical energy and the blue shows the heat and light energy. So in this process of hydrogen combining with oxygen, overall energy is released when these water molecules form. So what it wants you to do in the Chem Catalyst is really talk about each of the bonds that's broken. So there are two hydrogen bonds broken and one bond broken between the oxygen molecules. And that's a double bond. And since two water molecules form, there are actually four H2O bonds that form. 4 OH bonds, I mean. So we've got 1, 2, 3 bonds breaking and 1, 2, 3, 4 bonds forming. And we want to make sure our number of atoms is consistent. So I'm going to circle the atoms with red. 1, 2, 3, 4, 5, 6 atoms. 1, 2, 3, 4, 5, 6 atoms. So matter is conserved. So it says when you break these bonds, you need to put energy in. And this is a different reaction showing methane, CH4, combining with two oxygen molecules and forming carbon dioxide and water. So here we've got a little bit of a different situation because we've got 4 bonds breaking in that CH4 and there are 2 oxygen molecules. And so these arrows are showing the energy going in to break those bonds and break these two O2 bonds. And then these arrows are showing that as the new bonds form, energy is released. So you can actually quantify this. So there's something called the average bond energy per mole's worth of bonds. So if you had 1 mole of hydrogen bonds, of hydrogen molecules, it would take 103 calories to break those bonds. Also, in reverse, if you were forming 1 mole's worth of hydrogen bonds, it would release 103 calories. So looking for patterns here, you can definitely see right away that some of these bigger numbers on the chart, the 3 largest numbers, are double bonds. So double bonds require more energy to break them. And on the flip side, they also release more energy when formed. And you may have other patterns that you notice as well. So let's quantify this. How much energy would it take to break all the bonds of the reactants? Again, we've got a CH4 and 2 O2 molecules. So for each of those CH bonds, if we find that on our chart here, I'll write in green, it takes 99 calories per mole. So since there's 4 bonds, 4 times 99 is 396 calories. And for the O2 molecules, there's 2 of them, and it requires 118 calories per mole. So if we add all that up, I guess they didn't add that up, they just show 396 plus 236. That's how much energy is required to break those bonds. But we're going to get some energy released when we form the new bonds. And since this is combustion, we know that this is going to be an exothermic reaction, and overall it's going to be releasing more energy than we had to put in. So I'm just going to go ahead real quick off to the side here and add up 396 plus the 236. We had to put 632 calories per mole in to break the bonds. Okay, so here we're forming 2 C double bonded to an O bonds. So 2 bonds, and that's 191 calories released, so 382. And then for each of those 4 OH bonds, they're 112 calories each, so 448 calories. So 448 plus 382, 830 calories per mole out. We can say forming bonds. So overall then, 632 in, 830 out, that's a negative 198 calories per mole. So what's the significance of it being negative? Well, this is the energy that's released. And that's why this feels hot, because the formation of those new bonds is ultimately causing a, if we go back to this other chart at the beginning, more energy now is released as heat and light versus being in those chemical bonds. Okay. So in class, we worked on an energy story where the energy is coming from when fuel is burned in a car. And so people talked about how, you know, one of the main components of gasoline is octane, which is C8H18. And when that combusts, these all require energy to break the bonds, but ultimately the formation of these carbon dioxide and water bonds, this is lower in energy, and so there's an overall release of energy. And some people knew more about car engines than others, but again, the big takeaway here is that this reaction will release energy that's usable and can fuel our car, power our car. And so some other things that we did in class is just reflect a little bit on what we've learned about bond energy. And the homework questions have a little more practice with your thinking. So that's part of the assignment that you are supposed to do. So hopefully that helped you get a little bit of a grasp on what you missed.